All right, we're gonna go, or the homework problem. We're gonna look at the homework problem number 7 with Newton's method. Um, and so we're going to approximate the where a graph intersects. So I'm going to start by drawing the problem out with just a rough hand sketch, and then see what we want to do and why Newton's method is helpful for this. So I have two functions. The first one, f of x equals 1 over x. And the second one, g of x. Hey there, how you doing?
Are you good?
No, I'm not good. How are you? I still haven't. I have to, and I really need to pause this because otherwise I'm going to be recording this conversation.
Oh yeah, that would be bad.
Not bad, but
I was just,
well.
did you hear?
All right, so we have two functions here. So this problem sets up where x squared times x plus 1 for g. So I heard her talking in the hallway, and it was flagging me because this is her long day. All right, so we want to ask where these two functions are going to intersect. So if I draw f of x, it's going to look like this. And if I draw g of x, g of x is x cubed plus x, so it's a cubic function. Squared. It's a cubic function. It has a 0 at x squared, and it has a 0 at -1. It comes in from negative infinity and leaves by positive infinity. The 0, it's going to come up through here. It's going to bounce off this and go out through here. That's what these zeros do. And so this is the general behavior. So the points we want to find are these points. And so this is our mysteries that we're trying to solve with Newton's method, are these points. And so this is what the question is asking, or what are the points of intersection? And so if we're looking for the points of intersection, we have to put these functions together and find this point and to find this point. And if we look at the graphs of the function, 1 over x is our classic asymptotic function in the first and third quadrant. And then if we look at g of x equals x squared times x plus 1, all I did to sketch it was I looked at it was a cubic, and it's a cubic with a positive leading coefficient. So it comes in from negative infinity, goes out from a positive infinity. It has two zeros already, g of x. One is at 0, and that has a multiplicity of 2, so it's going to bounce off of that. The other one is at -1, so it's going to pierce through there. So this is what's happening with this function, and these are the question mark points that we need to find. So when we find where functions overlap, then we are asking ourselves the question of when does f of x equal g of x? That's what points of intersection mean. So we're going to scale these into a new function then, and we're gonna put them equal to each other. So I'm gonna have 1 over x equals x cubed plus x squared. I'm going to multiply both sides by x. Take care. And then I'm going to subtract 1 from each side. And so this is going to help me find the x values when these intersect. And so this is going to be the function that I'm going to try to solve.
What should we call it?
I'm going to just call it h. H of x equals x to the 4th plus x cubed plus 1. To use Newton's method, I'm going to need to know h prime of x, which is 4x cubed plus 3x squared. All right, I'm going to look at the Newton's method formulation of this in the form of my iterative process f of x of n plus 1 is equal to x sub n minus f of x sub n over the derivative of f of x sub n. Now, we can approach this a couple different ways. I can try to put this into an individual formula, or I can make some table values and put the table values together. I'm going to work on this in a tabular form, and you're going to see me run to my calculator a lot on this. So I'm going to do the number of iterations. I'm going to do what my function is at the x value. Oh, wait. I'm going to need the current approximation of x. What my function is. And what my derivative is. And then in what we're going to work out here then off on the side is each n plus 1 is going to derive the next x of n. So we're going to keep track of our x of n's down the side here. So I'm going to start with a guess. And if I look at my graph of a guess here, to get this function over here, I need to be greater than 0. To get this side of the function, I need to be less than -1. So I'm going to, in this example, try to find the upper intersection point. I'll leave it as an exercise to the viewer to find the one here. My guess for here would probably start with -2 or smaller, because that would put you on this side of the function, and you would work your way back to here, because we know this point is on this side of it. For here, because 0 is flat, I'm going to try a 1. So I'm going to try with 1, and we'll see how it goes. Sometimes these things can oscillate if we get stuck in a valley. But we'll start with 1 as our guess for x. And so we'll ask ourselves what the function is at 1. So, and this is where a calculator is nice. If you enter these in with parentheses on the calculator, so on my calculator, I'm going to put in 1 to the power of 4 plus 1 to the power of 3 plus 1. Every time I put in a new value, I can scroll up and use the insert key to put in the new value. I'm going to do the same thing for the derivative. I'm going to put in 4 times 1 to the power of 3 plus 3 times 1 to the power of 2. And I can continue to scroll up and change these values as they come across. So you'll hear me pause with the calculator as I work my way through each of these values. So if I put 1 into my function, I'm going to get 1 to the 4th plus 1 cubed plus 1. And that's 3. So the function is 3. And then if I put the
Wait, what? Wasn't it a minus? Cause there's a,
oh, it's the one negative? Yeah, it's a negative one.
to subtract the one.
Yeah, subtract the 1, thank you. I will do everything to fight so this ends up becoming 1.
I would've tried earlier if I wasn't looking.
Pardon?
I would've told you earlier.
No, you're good. Negative signs kill me. It is my bugbear. Someone. So let me come back,
You
fix.
want an erase tool?
I do, but the eraser is so small. I'm just gonna do this for right now.
You can turn up the.
Yeah, and it takes a long time for it to go back and forth between the two. I have an erase tool. I put the erase tool on, getting the size larger, and then in getting back to the right pen size, about a minute of fudging around. At least the derivative's still the same because the constant fell off, and so I'm going to have I'll enter. I'm still going to enter it in on my calculator, so that I can scroll up to it. So I'm going to have 1 cubed plus 3 times 1 squared, which is 7. So my x of 1 is going to be 1 minus 1 divided by 7. And I hope we can see the problem that starts happening here, and why we sketch the graph out a little bit. Because my next, my next value, this is going to be what, 6/7? 6/7. 6/7. So now we can put in 1 is 6/7. And so I'm going to scroll back up and I'm going to choose my function, and I'm going to, instead of leaving a 1 in here, I'm going to put 6/7 if my insert key works.
I'm so tempted to just do this out.
Oh, to get an easier formula? It's all how you keep track of it.
It's not easier in the slightest.
What? To do it out?
To get the next thing, to get the next one, it's, you're putting 6/7 into all of the powers. So
Yep.
So it's not easier at all.
Hence
But-
calculator.
Yes, but I'm so tempted to do it anyway.
Because yeah, and Newton's method has always been a computational thing for me. So calculators are both Newton's method and Euler's method. I did in exams for both calculus, ODE, and numerical where we had calculators. I actually learned to program them onto my calculator because they're coming through. But so let me go 6/7 to the 4th power plus 6/7 to the 3rd power minus 1. And I've lost my decimal or my fraction version of it. I'm going to get 0.169512703. I'm going to keep all the decimal places so I minimize my rounding error. And now I'm going to take my derivative of it. And so I'm going to take 4 times 6/7 to the third power plus 3 times 6/7 to the second power. And I'm going to get 4.7230 3207. So my x sub 2 then is going to be 6/7, I think my last fraction I'm ever going to see, minus 0.169512703 divided by 4.72303,207. You're still doing it out the long way? Power to you, my friend. And I'm now getting 0.8221252205. And so that's my x sub 2. 0.8212522205. And I'm going to stop at the third approximation for this, right? We want to see where this upper one can go. I went from a 0.85 to a 0.82, and I want to see. I'm going to look at the third one, and if I don't see a big change in the first 2 decimal places or the first decimal place, we're going to say we're getting closer. So let's take. My function is going to be, okay, so I have that my answer, so I'm going to have my answer to the 4th power plus my answer to the 3rd power definitely have to 0.82 wait a minute, my function's wrong. Did I flip those around? That shouldn't be 0.1695. Is it 6/7 cubed? Oh, I forgot my -1. That's why I forgot my -1. On the one I'm doing right now. I forgot my -1. So let's see, 0.8212522205 to the 4th plus 0.8212522205 minus 1. And so now the function at this point is 0.008787603. So notice how close our function is to being 0, right? We want to find when this function is 0, and at this point it's within 1,000th or 8,000ths of being to 0. It's almost 100th within there if we round. So let's do f prime. 4 times 0.8212522205 to the 4th plus 3 times 0 point, or not the fourth cubed, do my derivative. Trying to use a calculator and talking about it so that the video heads can do this. I wish I had an Elmo here, I would just show the calculator. Squared. Let's make sure I have 3 times this. I get a 4.2 for my slope. Where are you at, Sarah? On your are you on x2 still?
Yep.
What did you get for the function? Was the function fairly small? Number. What's the number?
What do you mean?
So for the function at x sub 2, what did you get for it? You got a fraction?
I have, like, I'm not done with it.
So you're working on this part of it, or are you doing all of it at once?
I put the 6/7 into the things.
Yep.
So I'm doing it out and keeping it as fractions.
Yep.
So I'm getting big numbers that take a while to multiply because I'm doing it all by hand.
I understand that, yeah, but so you don't have the fraction for f of x right now.
I'm not doing it that way. I'm doing it in x of n plus 1 equals x of n minus x of n to the 4. I'm doing the thing all as a whole. Not
You
as
substituted the
individual
x of
columns.
n's in for this, right? You're doing it as a whole, not in the columns. Got you. Okay. All right. I will.
So I don't have intermediate steps.
Well, I'm going to stop at x sub 3 then. I'm going to see what x sub 3 gives us. So I'm going to have 0.821252205 minus the fraction of 0.008787603 over 4.2389567 And I think this might be my last approximation for this. Yeah. 0.819249919. And so we can see we're around 0.8 as a value through here. And you can keep continuing this. This is not always meant to be the best function, the best for doing it by hand. I mean, Newton did do it by hand. That's what he had to deal with. But let's look at what we can do if we let a spreadsheet do the work for us. So what I want to do is I'll make a function for my zeros and ones, and so I will, in a spreadsheet, say we'll calculate this down 10 times. We're going to start with x sub n. We started with an estimate of 1. And then we're going to want to calculate our f of x our f prime of x, and that'll help us calculate the other versions. So our f of x was our x sub n to the 4th power plus our x sub n to the 3rd power minus 1. And our f prime was 4 times our equal 4 times our x sub n to the 3rd power plus 3 times our x sub n to the 2nd power. So here we have the ability to continue to create these. And what we want to do now is make a chain that links these together. So our next x sub n is this minus this divided by this. And so there we get our estimate. So what we can do is we can use this estimate to generate the next values. And as we keep copying down, our spreadsheet keeps getting our approximations better for us. And so this matches what we did by hand here. As we work our way for each values, we can continue to get better. And in about 4 steps, it looks like we've got a really good estimation. In fact, in 4 steps, we get it to the point where we're not really seeing much change in the decimal places. So our spreadsheet takes the place of our calculator, and this is where Newton's method really comes in handy, as computational tools can quickly calculate a lot of decimal places for this. By hand, it's a little frustrating, but if you ever need to plug something into a computer, understanding how you do it by hand is what helps you for this. And like I said, Newton's method is usually the first thing you'll get in a numerical methods class or a computational methods class, is that you'll have to learn to find roots this way. And so this was the positive root. It's around 0.819172513, and that's about as good as we're getting in 5 steps with Excel. Which was close to what we did by hand in 3 steps. We were at 8.192 as we continued our way back. Again, that is the first guess. It was for the positive one. You could start a very similar guess with -2 and see where -2 gets you. All right, I'm going to stop that recording there.